So welcome everybody. This is the 7th talk in the series, COVID motivated series. And I think one good thing is that we could do this and do it in a bigger family of people. And as usual, there will be questions during the meeting. You can put them on the chat and I will try to bring it to Nick whenever I find a chance. And the rest will be towards the end. Please type your questions in the chat to me. And I think without further ado, let me introduce Nick Bronn. Nick did his PhD in 2013 in University of Illinois, condensed matter. And please mute your mics. And then he moved to IBM basically since then, initially as a postdoc, I think, and then as a, I'm not sure what the title exactly is.
Research staff member.
Research staff member. And he's been working in different and exciting things. We had him at CQT a year or so ago. Was a different era at the time. It was quite nice to be here and so on. And today he will tell us about the recent developments in doing pulses using the cloud quantum computers. And without further ado, Nick, the floor is yours.
All right, well, thank you very much for that introduction, Dimitris. It's a pleasure to be back here, albeit virtually. I don't get chili crab this time, unfortunately, but I'm happy to be here nonetheless.
Exactly.
So, last year I talked about the different devices, device metrics and benchmarking, and since then we've had a lot of exciting things happen in the realm of pulse level control of the quantum systems. And this is some really exciting stuff it's ongoing, but it's also very recent, and I'd like to touch on what we're doing at IBM today and why is this useful and why is it interesting. So please feel free to ask questions, and I'd love to answer them whenever you think of them. Okay, so first thing I'd like to do is kind of go back to this picture of the this first Physics of Computation conference, which was co-hosted by MIT and IBM in 1981. Most people just go and talk about this because this is kind of the idea where Richard Feynman thought it would be great to have a quantum computer because you could simulate nature better, like say nuclear interactions, molecular interactions. The Hilbert space gets too large for any classical computer to handle these kinds of problems. So you need a quantum computer, or a computer that obeys quantum mechanics in order to solve those. But what I think is more interesting is actually this is a break from treating computation as kind of an abstract mathematical concept, one that took classical computing very far. When people started thinking about the actual physics of what was doing the computing, they started coming up with thermodynamic theories. They started coming up with ideas of quantum computing as a way to maybe do irreversible computing with no entropy increase. So pretty much what I want to go to today is talk about the quantum computing you may learn in your classes and stuff like that. But how does that actually apply to the actual physical systems, and how do we implement control of these physical systems? So, let me introduce the Qiskit, which originally stood for the Quantum Information Science Toolkit. It's developed by IBM, and it is an open source framework for quantum computing. So mainly, it's open source Apache license, it's written in Python, and it's meant to be modular and extensible. It sits on top of any hardware, in particular the hardware that we have at IBM. But it also can sit on non-IBM devices, and it has been employed from other companies on non-superconducting hardware, for example. Mainly, Qiskit involves the bedrock of the elements of Qiskit is Terra. And this actually is a bunch of tools to build, run, and take quantum circuits and compile them into something that can be understood by a hardware backend. So this is kind of the guts of everything, but then we've built libraries on top of that, mainly for research, such as people trying to characterize and mitigate errors, because we're in the noisy near-term quantum hardware era. We're going to have lots of errors and we're stuck with them for now. So we need to figure out how to get better at getting rid of them as we make the qubit hardware better itself. We also have an element called air, which is special purpose simulator. So we can put in noise models, your full, Lin-Blodian master equations to try and figure out how well your systems may be able to perform on the actual quantum hardware. And then we have Aqua, which is mainly a framework of libraries for domain experts in fields other than quantum computing, such as artificial intelligence, finance, chemistry. So these are kinds of things where, say, you're a quantum chemist and you don't really care about how a quantum computer works. You can just go in there and start taking molecular models and putting them into a system that will eventually compile down and be run on a quantum computer. So today, what I'm going to be talking about is a newer part of Terra called Pulse. Oh, I'm not quite there yet. You can easily install Qiskit. We make it as easy as possible for you to install by using a Python package manager. We have it available on GitHub. It's open source, so you can contribute to it. We have outside contributors as well, and we have a Slack community. We have many Slack channels where we can answer questions and build communities and projects that we can do together with outsiders as well. The part of Terra that I wanted to tell you about today is Pulse. So this is built on the Open Pulse specification, which was released a few years ago in a document that's available on the archive. But mainly this is going to talk about the newer results, which we're calling Qiskit Pulse, and how we can use that to start doing interesting things with the qubit hardware at a very kind of experimental level. So this in particular is the archive paper I wanted to reference that came out in April. And these are a bunch of developers that are working on it at many of our different research centers. And I was thinking about it because if you look at it, the main motivation for having Pulse was actually achieved by a number of other recent research articles. For example, one of the reasons you might want pulse level access is for optimal control. Well, just back in March, we had a collaboration with Frank Wilhelm's group in reducing leakage. Leakage is when you apply a pulse to go from the 0 to the 1 state and you accidentally excite into the non-computational 2 state, which is actually very bad for things like error correction. So this is something we try and obviate against, but using optimal control, you can do a really good job of it, and they were able to realize a 4 nanosecond single qubit gate, which is a lot faster than what we typically do, 10 or 20 nanoseconds. Another example is error mitigation. So what we can do is, in this case, this is a classical error correction technique that was relying on a scaling factor of the incoherent error in our computations. And this was published in Nature last year as applied to, well, chemistry is what I'll show you about that today, but some other systems as well. Additionally, pulse level control might be good for dynamical decoupling. This is kind of more of a quantum error mitigation, where you can use the dephasing that occurs naturally in a system, and you can kind of echo it out in a way. And this was just published just this month of a technique we call rotary echoes for reducing spectator errors and other kinds of coherent errors in our cross-resonance 2-qubit operation. So I think this is very nice to see, the Qiskit Pulse be applied and be able to apply to systems so quickly after its kind of debut. So what's the difference between pulse and circuit? So the first idea is in Qiskit, the first thing you'd probably want to do is create a Bell state. That's usually what I do whenever I start playing with a new system. And you can do that by putting, say, qubit 0. It starts in a 0 state. You can apply a Hadamard, put it in a superposition of 0 and 1, and then applying a CNOT between that and the Q1. Will create a 0, 0 plus 1, 1 state, which then you can measure. That measurement collapses the system from a quantum system to a classical system. So you go from single bars to 2 bars, and that measurement gets dumped into a classical register. So this is kind of the most basic kinds of thing you might want to do in Qiskit, maybe an idea of our hello world kind of program. But what actually happens when you do that, I mean, this system gets, it gets transpiled, I'll talk about that later, and then gets scheduled into a series of pulses. And that series of pulses looks like this. And this is just kind of a mess of a bunch of things going on a different number of channels. So I'm gonna eventually come back to this and explain to you everything that's going on here, because it's all available and knowable from kind of a pulse level control kind of way. So taking a step back, I'm just gonna kind of give a review of the anatomy of a superconducting qubit and how we control them, and then how we use pulses to control them. So basically, we have superconductors consisting of niobium and aluminum, which lose their electrical resistance when you get them cold enough. This is a 5-qubit device that we made at IBM, and if we zoom in on those little square pockets, we can see the qubits, which are represented by these 90-degree rotated equal signs. And that equal signs actually forms the capacitor of the circuit, and between those two lines, you'll find a special element called a Josephson junction, which acts as a nonlinear inductor. So what you have is a nonlinear LC circuit, essentially. We also have more linear LC circuits, which are these microwave transmission lines, which we use to connect the qubits together to couple them and entangle them. We use these for as filters for the qubits because they're impedance mismatched to the qubit frequency. So they can act as filters. And we also use them for readout because we can hybridize the qubit states and perform measurements based on that. But basically what happens is these microwave resonators are like linear LC circuits, and just like you know from either your circuits class or your quantum mechanics class, a simple harmonic oscillator is going to have evenly spaced levels. Well, that's a problem for quantum computing because you can't encode the say the ground is a 0 and the 1 is an excited state, because when you try to drive between them, you'll leak into the other states that are higher above. Because they have the same energy, they're not differentiable from each other. However, when you have a Josephson junction, you have something we call an anharmonic oscillator, where the difference between 0 and 1 and 1 and 2 and 2 and 3 are all different, so you can uniquely specify the energy levels. And I should also specify this is a specific type of superconducting qubit called a transmon that is essentially this anharmonic oscillator, and it's kind of one of the easiest to understand, and it's also, I would say, the one that everyone kind of pursues if they're trying to build a quantum computer because of that. So we can address this energy gap, which is about 5 gigahertz. It's the transition frequency between our 0 and 1 state. And if we multiply that 5 gigahertz by Planck's constant and divide it by Boltzmann's constant, we see we're at a temperature of 240 millikelvin. So in order to have a narrow enough state in which we could do quantum computing, we need to be substantially colder than the line width of radiation at 240 millikelvin. So we need to go even colder, and we actually go to fridges that have a temperature of about 10 millikelvin. So, what do we do with those superconducting qubits? Like from a mathematical standpoint, I try and connect the mathematics and the physics of what's going on so it makes more sense. So we're just going to return to the Bloch sphere, which I'm sure you all know. We use 0 or 1 in Dirac notation because we're lazy physicists, but those just stand for the column vectors 1, 0 or 0, 1, which are represented by the north pole or south pole of the Bloch sphere. We have these Pauli matrices, which represent the basis in which we can perform measurements. For superconducting qubits, we can typically only measure in the Z basis. So we know that we can see that 0 is an eigenstate of Z with the eigenvalue +1, and 1 is an eigenstate with eigenvalue -1. You could also measure it on the X and Y axes in different systems, but typically not superconducting systems. But these Pauli matrices can also generate rotations around the Bloch sphere. In fact, by any unit vector n, you can essentially, you can write down a unitary for a rotation of an angle theta about it by exponentiating this matrix, which is the unit vector dotted with a vector of the Pauli matrices, and you get this nice little compact formula. So it's very easy to write down unitary matrices. So for example, theta rotation around the x-axis is given by this unitary matrix right here. So you can see how these act on the actual Hilbert space. So what do we do in the lab when we want to do that? Well, we apply microwave pulses. So these are typically microwave pulses with a Gaussian shape that have a carrier frequency at the transition frequency of the qubit, so like 5 gigahertz. And then we typically put a derivative component on the quadrature, something we call a drag pulse for derivative removal of adiabatic gate, which helps prevent leakage to the 2 state, because the transmon is not actually a qubit. It's got many levels, but we want to confine ourselves to the 0 and 1 level. So what these microwave pulses do is they just rotate you around an axis in the XY plane of the Bloch sphere. So the only difference between an X rotation and a Y rotation is the phase is 90 degrees shifted between the two, which kind of leads us to another trick that we do. How about Z rotations? Well, we can compose that out of X and Y rotations, but we can be even trickier, because what we can do is we can get those for free just by compiling the circuits that we want to perform and just shifting the phases of the subsequent pulses. So by compiling these in software, we get pulses that we get essentially gates that come for free. So when we do randomized benchmarking to calculate our single qubit error rate, we get a lesser value than what we would if we were actually doing the Z rotation. So like I like to say is the only perfect quantum gate is the one that you don't do. So this frame change thing you'll see is something we're always using. The other thing we need for a universal quantum computer is a universal gate set. And for classical computers, you may have learned that you can either pick the not and or not or gates. What these are just inverses of the Boolean and or gate. And you can construct these in CMOS, and you can construct any logical Boolean thing out of either of these gates and scillas. We have a similar situation in quantum computers where we need single qubit rotations, not even all of them, but just a subset of them. And two qubit operations such as their controlled NOT operation. So this is kind of where things start getting entangled, is you can use a controlled NOT to act on a state of 2 qubits where the first qubit is called a control qubit, the second qubit's called a target qubit. And essentially what happens is you do a NOT if the control qubit is in the 1 state. So if it's in 0, nothing happens. 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. But if your control qubit's in 1, then you flip the other one. So 1, 0 goes to 1, 1, 1, 1 goes to 1, 0. And you can see that this generates entanglement because you can start with a qubit state. Say, for example, let's see, what would I do? Like, if I took a superposition of 0, 0 plus 1, 0 and did a CNOT, then I would get 0, 0 plus 1, 1. So you can generate a Bell state in that way by putting the input in a superposition state. But that's not the only one you can do that's universal. You can also have a controlled phase. And what this does is it just puts a phase of 180 degrees or a minus sign on the state where both qubits are in the 1 state or the excited state. You can also have something called an I swap, where you swap the states of the qubits. And if it's not trivial, you get the imaginary number I in front of it. So that's why it's called an I swap. And each of these are essentially dependent on the physics of the superconducting devices. And this is where everyone has a different opinion of what gate is kind of the best. And this is where the architectures do differ between people who are trying to build quantum computers. So let me tell you about what we're doing at IBM. We use something called the cross-resonance gate. And essentially what the cross-resonance boils down to is it's a ZX operation. And the ZX is actually up to a couple of single qubit rotations. It's a CNOT. So that satisfies the universality. Essentially what it is you take the Z and X Pauli matrices, tensor them together, and you get this bigger matrix right here. But what happens when you exponentiate that matrix, the rotations you get are going to be such that they rotate the target qubit dependent on the state of the control qubit, which sounds a lot like a CNOT. And just by looking at this matrix, you can see here in the upper left of this unitary, you have an X rotation, and that corresponds to the subspace in which the control is in a 0 state. And in this lower right subblock, you can see that that corresponds to where the control is in the 1 state, and that's a negative X rotation. So if you look at the Bloch sphere, we can consider each of these separately and then see what they do together. If we just consider the control qubit in the 0 state, the target qubit starts in a 0 state, we apply the cross resonance, the target qubit starts rotating to the right. Okay, if we forget about that now and prepare our control qubit in the 1 state, so it's blue, the target qubit starts in the 0 state, and we apply cross resonance, the target qubit will rotate to the left. So then what we always do is we can apply this to a superposition of states. So we'll try it to the 0 plus 1 state. And then what happens is our target qubit will both simultaneously rotate to the left and the right at the same time. And if you do this for an angle of pi over 2, you get a perfectly entangling gate. So this is kind of the basic, and this is essentially the interaction that we want to isolate for our cross resonance gates. And it gets a little bit more complicated than just the ZX, but what we actually have here is it's all microwave, so we don't have any kind of tunability. We don't have couplers. We don't have tunable qubits. Everything is fixed frequency, and that lack of tunability is what helps us have very long coherence times for our qubits. And so we like this kind of all microwave thing because it's fixed. Not that it doesn't have other problems, but we like it the best. So essentially what we'll do is we'll take one of these microwave transmission lines and couple 2 qubits with it. And that coupling will happen at a rate J. So that's kind of hybridizing the qubits together. So what happens if we want to do a rotation of qubit 1? Well, we apply a frequency at qubit 1's frequency. If we want to apply a rotation of qubit 2, we apply a pulse at qubit 2's frequency. And here's where one of the tricks about the cross-resonant gate comes out. Well, I told you we make these Josephson junctions on an earlier slide. Well, essentially it's a superconductor insulator superconductor barrier, and they're typically, aluminum oxide, aluminum. So that aluminum oxide layer that you grow, even across an entire chip, everything is amorphous, so it's going to grow differently. So the critical current through each one of these Josephson junctions is going to be a little bit different, which means the frequencies are going to be turning out a little bit different. So in general, the frequencies of Q1 and Q2 are not going to be the same. And this is actually very important for the operation of this cross-resonance gate, because what we're going to do is we're going to drive the control qubit at the frequency of the target qubit. So we're actually applying omega 2 onto omega 1, which is why we call it cross resonance, because it's resonant with the opposite qubit. And why that actually does anything is if we look at the energy level diagram of the two qubits, if you look at the dotted lines, that would be the two qubits not interacting. So that would be without the microwave resonator bus coupler between them. But as soon as you have this coupling between them, the qubit states hybridize. So the 1, 0 and 0, 1 states will shift away from each other in energy by an amount J squared over 2 delta, where delta is the detuning of the difference in frequency between the two qubits. And then because these are hybridized in different directions, we can try and drive these transitions between the control being in the 0 or the control being in the 1, and we pick up a different sign difference because of this difference in hybridization. So this is essentially what causes that effect of the ZX to happen. So that's basically the physics picture of that. But we'll get into that a little deeper. So what happens in the lab is, say we take a computer and we use Qiskit and we tell it to apply certain pulses. So for example, in this measurement pulses to measure qubit 0 and store it in classical register 0, qubit 1 and qubit register 1. Those signals get mixed together with RF generators and arbitrary waveform generators and then sent into a dilution fridge down to the coldest stage where we have the qubits live, and they interact with the resonators that are coupled to the qubits. And essentially, the qubit state imparts a phase shift on that resonator frequency, and it gets sent back, mixed back down, and analyzed by a computer to see whether you measured a 0 or 1. So that's kind of a literal cartoon picture of how a measurement process works. But this kind of goes the same with control pulses as well, except we don't get them back on the other side. So for near-term quantum devices, there's kinds of a lot of hardware solutions we know make your qubits better, make the coherence times longer, and make the gate operations less error-prone and reduce the crosstalk. But there's a lot of control solutions that can help us there. So some of the hardware solutions we have, such as the frequency crowding, this comes from the inherent fact that we're using fixed frequency qubits. So we only have a limited amount of frequency space in which to do this addressing. Of course, crosstalks and the robustness of the qubits is important too, but we can get around some of these errors with certain kinds of measurement calibrations, with shaping pulses in better ways, such as drag would be one of those examples of pulse, or that's kind of an analytical pulse shaping. For hardware gate sets, we can engineer coupler Hamiltonians. We can go crazy and make everything tunable, and you can get all kinds of terms in your Hamiltonian. And that can be very interesting physics, but it can also be kind of a mess when you're trying to control things. You can try and approach the hardware gate sets from a different angle, such as pulse shaping. There's a number of different, the cross resonance is not the only 2 qubit fixed frequency microwave gate. This is still kind of an area of active research. Then we can look at the number of parallel operations we have. So there is crosstalk. We've published results on our spectator qubits, which are qubits that are whose frequency is affected by the states of the qubits they're coupled to, because there's kind of an always-on ZZ interaction between the qubits that's mediated by that coupling J. But there's certain things we can do, and I'll show this later, especially with that rotary echo. There's certain things about pulse shaping and scheduling that will allow us to get around certain problems. Finding clever ways to cancel out the interactions that we don't want is one of those tricks. So let me get down to what the pulse programming in Qiskit is. So I showed you where the pulses come from, and we'll get a little bit more into the cross-resonance pulses later, but basically you have the idea. And we separate those pulses and put them on certain things we call channels, which will eventually correspond to a physical channel in the lab, like the output of a AWG that goes into a fridge that is coupled to a qubit. And these consist of drive channel, which is essentially an on-resonant single qubit control, which is aliased by this little DI, which will be the essentially the DI is the wave form at each instance of the waveform generator. So it's dependent on the time step of the waveform generator. There's another channel called the control channel, which is similar to the drive channel, but it's usually used for off-resonant control, such as cross-resonance, and we just separate that out to have a on-resonance, off-resonance control. And those will typically be at different, but not that different frequencies. Our measurement frequencies will be very far from the qubit frequencies and cross-resonance frequencies. And we can also control those measurement frequencies as well, if we care to. It's something that we kind of tune up as a default. I mean, everything we give you, you can use as a default, but you have the ability to go back and change it and explore more device physics by choosing your own pulse waveforms. And then we have the acquire channel, which is not actually pulse itself, but it's just kind of tells a digitizer to acquire a signal that's coming back from a measurement signal. And then we have commands that kind of instruct what the pulses can do. So you can play a pulse out. That's simple. You have a Gaussian, you play a Gaussian. You can make delays between different pulses. You can change the phases and frequencies of the pulses themselves, so the carrier frequencies, and then you can look at the acquire channel, and you can actually do a number of things with the acquisition that you get. So as kind of a schematic of what this looks like is, you have the drive channels and the drive channels and control channels would be mixed together and sent to your quantum device. And what Qiskit Pulse does is this isn't exactly how it works in the lab, but we try to most faithfully reconstruct what you are, instructing the qubit to do. So we will have some sidebanding here, for example, whereas you'll specify the envelope in Qiskit Pulse, we will try to create the waveform that looks most like that. And then we can look at acquire channels, and once they're in registers, we can do other things to them. I'll get to that in a sec. So essentially each one of these values that you can specify in Pulse is a complex value. So there's an n-phase or quadrature, as we like to say in the microwave world, components. That just means complex numbers. And each one of these is played for an interval dt, which is essentially determined by the maximum sampling rate of the waveform generator itself. So for like our really good systems, one of which is publicly available. This is like 0.22 nanoseconds or so. So it's pretty high bandwidth. These values are going to be modulated by an envelope, which is specified by a tuple of frequencies, typically the resonant frequency of the qubit you're driving at, and phases, which can be something that changes, such as that frame change. In order to do Z rotations, you can just change the frame, and that's kind of how you do it for free and in terms of Qiskit Pulse. So what you end up getting is these capital Ds, which are the real part of this modulated waveform, and then you can write down your Hamiltonian as the system Hamiltonian, plus all the drive terms that you get from the pulses that you're applying. And this is kind of the way we think of, yes.
Nick, just a quick question on this.
Sure.
So this is really like a time-dependent term, a drive, like a proper drive, as we call in quantum optics, in this extra HI term. So this could be something like cosine FJTT something, a modulating term. What is HI? HI could be, what is H system and HI in the circuit level in your digital?
Okay. That's a great question. So if I was telling you and we were limiting to ourselves to cross resonance, it would be the ZX interaction, for example. But really, it's all the interaction terms that you can get out of that Hamiltonian that can be, driven interactions from that. So I guess what I like to think of, because I was just teaching the intern summer school, is you can think of the drive as acting on a qubit in a way by going by doing the rotating wave approximation and then moving into the frame of the drive. Then you can see that you have like a drive term that corresponds to X rotations around the Bloch sphere and a drive term that corresponds to Z rotations, or an undriven term corresponding to Z rotations.
In the Hamiltonian language, in the rotating frame and so on, it's all kind of clear. But it's not clear to me when you go to the gates, how does this look like in the system, in the Qiskit level? So if we manipulate, if I write down a Hamiltonian, the H system could be your ZZ interaction or XY interaction, whatever is natural there, fine. And then now you put control at the hardware level to modulate this from the outside, let's say the X magnetic field. But how, maybe you're going to say that later or something.
Yeah, I think I see what you're saying, and that's it's kind of a there's kind of a difference, and this is something that we're kind of working on rectifying, is that in the gate level, right now we have kind of the we call open chasm, which is the quantum assembly language, and we have the open pulse specification, which is the specification for these pulses, and the way you build them is kind of different, and they're kind of like two different things. So I think you'll kind of see how we mix them together later on. But once you're kind of at the pulse level, it's really hard to go back to the circuit level.
Exactly.
Because
well, you need all the intermediate marks. You have to digitize maybe the circuit and do some sort of digital version. I mean, we can go from analog Hamiltonian version to digital circuit level. We know how to do that, like the transformations are there, but you need to do the calculation. It's not obvious now at this language level. At the Qiskit level, this is not there yet. This is what you're saying.
Right. I think we have that maybe for simulators. This is also, we're trying to beef up our quantum information libraries as well. So we can take, say, a given unitary and turn it into gates. So that seems like a more difficult way to go. What I'll be kind of showing in this talk is how we can take the pulses, so the gates themselves, and then turn them into a pulse language. But we can go kind of back and forth and define our gates in terms of the pulses, and I'll kind of be mixing this up in the talk now.
Right. Okay.
But I think what you're saying is completely possible, but that's kind of not the way we're thinking about it right now.
Okay.
But yeah, very good question.
Cheers.
Okay. Yeah, so I guess that's an overview of how this works, and essentially for simulators we can model these Hamiltonians and stuff like that. I mean, there's still a lot of work to get everything kind of completely on the same page, but
you know what I mean? Like let's take a simple case. You have 2 qubits, right? And you want to do a control node, right? If at the circuit level you put it there, you do your control node. Now let's say now you want to do that while you're timing the J coupling in your interaction, so some sort of sinusoidal behavior or something. I understand that. I mean, this is always possible at the hardware level. Experimenters do that, but that's how you on and off the J coupling, and then you do your. Now this what you're showing us here is that it's possible to do it also from outside to some level. You can manipulate the Hamiltonian, but if I go back to the circuit picture with gates, what does this mean in my normal programming, in my normal, like when I teach this, let's say to my students and say, this is the gate, the circuits, now we're going to put time dependence. How does that look like? Or are you going to explain that later on? Or maybe?
Right. I think I'll kind of touch on that, and maybe if I don't get it quite right, but basically what we're doing experimental wise is tuning up the gates by performing certain experiments like error amplification to try and find the best gates that you can use in your circuit model. Whereas now we have pulse access, you can try and tune up gates in different ways, and that's what this is done, and this is what other other people are trying to do as well. So I'll show some examples of this. But what this kind of blending in a way says you can define your own cross-resonant pulse, or you can define your own like optimally controlled leakage-free single qubit pulse, and then you can bring that back into a circuit model and do like quantum process tomography on it or something like that, and have the full kind of power of the circuit model on your pulses. So there is a way you can kind of switch back and forth. It's still maybe a little clumsy right now, but it's something that we're absolutely working on.
All right.
So let me see if you still have questions. Well, I'd be happy to talk about it more.
Yeah, please go ahead.
All right. So I want to talk about kind of the basic device characteristics. I'm sorry, this is already outdated because we just put some more systems online. So right now, let's see, I think it's 22 deployed systems we have on the cloud, and of those 22, it's 8 or 9 are publicly available. And they have kind of different topologies and different number of qubits. This is something we've been working through over the years to try and develop an architecture that works well as improving the qubit device performance. And over the time on the x-axis here, you can kind of see where we're going with coherence. We're up here around So this is a year old already. So we're like 100 microseconds, above 100 microseconds for T1, T2. And the error rate is down to more or less like 0.1% for single qubit gates and 1% for 2 qubit gates. So this is kind of where we're making the improvements as we're going into the pulse, as we're improving everything and enabling pulse access. And so in the long term, we had this kind of idea of how do we build like a fault-tolerant quantum computer? Well, you need to have a logical layer built with logical qubits that sits on top of a physical layer, which consists of physical qubits. And they'll interact with each other via a logical quantum processor and quantum error correction, where essentially your algorithms that you want to run are at the very top. But however, we're in the noisy near-term quantum error. And so we're only dealing with these physical layers in the bottom. And in particular, the kinds of instruction set architecture that we have via Pulse is just classical control of these physical layer implementations. So what you can do is you can specify either a pulse level instruction or a chasm, like a gate level instruction, and that will essentially get compiled down to the pulses in a device-aware way, and then put, such as a device-aware way saying, as I know, I have superconducting qubits and I can do, any rotation will be composed of a Z x pi over 2, Z x pi over 2, where the Z's are the frame changes and can be arbitrary rotations. I can generate any global unitary with that. So that's my kind of device level aware, and then specifically that corresponds to a frequency of the qubit I'm actually applying it to, and a certain amplitude of that pulse that will flip a 0 to a 1. And these are the kinds of things that are calibrated and that are kind of like given to you in the gate model. But that's done by physics experiments, and this is kind of done, maybe I would say from the bottom up is the right way of thinking about it. So what are the kinds of things we do when we go from something like the circuit to the pulse model? Well, each one of these pulses on the left here corresponds to something different. So the drive channels are going to be in the D, so that's going to be on qubit 0, and 1 on qubit 1. And these measurements and acquires are going to be in the red and the gray over here. So this just means we're measuring both qubit 0 and qubit 1, and we're acquiring on those channels. So you don't need to worry about those too much. But what we have going on here is, let me say, first of all, we have the cross-resonance tone is happening. And I can tell here that the cross-resonance is actually reversed from the direction of the CNOT, because we're applying it to qubit 1, and that'll be happening at qubit 0's frequency. But you can construct a CNOT by putting Hadamards on the ends of those, so you'll have some extra gates on the end. If you look a little closer, you can see these little loops here. These correspond to the frame changes that we're doing in the software. So this is kind of your like compiled circuit into what we would actually execute. And these are the ones that come for free, and this is kind of why everything's kind of broken into a ZX, because we can tune up a very good pi over 2 pulse, and that's the physical one we do. We can parameterize that as well, but usually you'll get mixed results due to things like mixer skew and any nonlinearity in your actual physical system. We also have the drag pulses. So these look like the derivative of the Gaussian, which are applied to the quadrature, or really just like if this is a real pulse, then you apply it to you add it to the complex part.
Right.
And oh, go ahead.
A quick. So the blue ones, the D0, for example, this is, can you remember this is the local frequency that you shift up and down, the omega 1 and omega 2, or what was it? So some of them are local frequencies that you change in time, and some of them were the J.
Actually, all of these are constant frequencies. The D's correspond to the resonant frequencies of the qubits themselves, and the U channel can be any other control channel. But this is if this. I know this is a cross-resonance pulse, so I know the frequency of this U1 is actually going to be the same as that of D0, because it's the cross-resonance.
What is the vertical axis? What are you changing?
Oh, vertical axis is well, it's amplitude, but each one of these channels is just.
So you change the amplitude of the pulse in time, basically.
Right. And I'll show you, because these are kinds of canned pulses that we have. Like you can specify a Gaussian pulse, a drag pulse, which will be, it's kind of an analytic way of getting rid of leakage. So you take the derivative of the Gaussian pulse and you scale it by a factor.
So in the control pulse, let's say if I do a pi over 2, if you can shape it, you can shape pi over 2 at different shapes. You can do like square, or you can do some sort of Gaussian and so on, and then see how much you really flip, if you flip properly, or if you have some population loss to higher states because you're doing too fast or too slow. So you can do traditional quantum optics at the level of the Qiskit now. That's what you're saying.
Exactly.
Okay.
And what I'll show you now is you can take those different pulses or whatever, and you can define them for your backend so that you can do like a randomized benchmarking sequence where Qiskit will know where to put the Cliffords, and it will put the gate that you defined inside of those sequence of Cliffords, so that you can figure out what your error is for those gates. And you can usually see leakage pretty apparently in RB as well.
Right.
So that's absolutely right. So these aren't even very fancy. These are going to be, you know, fixed frequency along each of these lines. That doesn't have to be the case. This is just kind of the canned way, the easiest way we can, you know, kind of make the best performing gates on a regular calibration schedule that doesn't take up too much time. So there's, you know, cool. And this is ongoing. We're always developing more kinds of tools for doing this. Like drag here is good, but we know you can do better using, you know, optimal control methods. There are some other ones. I guess that the echoing is one thing that we do standard. So we'll apply if you do a pi/2, you know, ZX rotation, which is a cross resonance, we'll split that into 2 pi/4s, and we'll do a positive pi/4, then echo it and to do a minus pi/4, and that helps get rid of some of the actual interactions that come along in the Hamiltonian that we don't want to deal with. And then this is the
one question from the audience.
Please.
Bartis, also from CQT. How much is the leakage error for the drag pulses? How much is the leakage error for the drag pulses?
Oh, what is the? That's a great question.
I guess it depends on the pulse, right? I mean, ideally,
yes.
drag is, you do drag to avoid leakage. Like if you do square, let's say, then definitely you're gonna excite to higher levels if it's too fast and so on. And ideally, you need to optimize it to some level. So
yeah,
you're doing drag to reduce, but I guess what Kisser is asking, like ballpark, like you have any?
Yeah, I'm afraid I actually don't have a ballpark number for that, because we usually use randomized benchmarking to characterize this, and basically the way you know that you have leakage is that your randomized benchmarking doesn't decay to the mixed state, so you're going to be off of 0.5.
Right.
And I don't know if we quantify that, but that's a great question.
All right.
Maybe I'll have to talk to someone and get back to you.
Yeah, usually after the talk we have a chat and we can.
Yeah. So yeah, absolutely, we can talk about that.
Please go ahead.
Yeah. So, and I'll talk a little bit more about the leakage later as well. So then the other kind of dynamical decoupling technique we're using is rotary echo, where we're actually constantly applying a in-phase IX, so non-conditional rotation on the target while we're doing cross resonance on it. And we find that for a lot of errors, such as spectator errors and other terms in the Hamiltonian, this will help get rid of those undesired interactions. And this is kind of different. This is something that evolved because in the last paper we wrote about this, we were using an active cancellation, which was trying to just add a tone that was the crosstalk pulse that was out of phase, that was reaching the qubit. So we found rotary echo can be a bit better, and I think I'll say a little bit more about that later as well. But the important thing is I wanted to show you that each one of these pulses gets decomposed into something that's meaningful, and we're using kind of these canned calibration routines to provide the best kind of gate pulses. So this is essentially what comes from canned. So then you can think about like, well, what if I want to come up with my own cross resonance pulse? And that's exactly what my developer friends did. So to just take a little bit of a step back, we start with a quantum circuit. So this is your Qiskit for generating a Bell state, and then we do something called transpiling. So we call it transpiling because we're not compiling the circuit to pulses, but we're transpiling the circuit to the native gate set of the device itself. So for superconducting circuits, we use these U gates, which are the ZX pi/2, ZX pi/2. If you wanted to compile to ions or something like that, this could be completely different. So all kinds of different architectures, you know, maybe sometimes they feature better global gates, and you know, such as ions, where they can do they have all-to-all connectivity, so they can do very quick entangling. But for this one, things don't change very much. We just change our Hadamard into one of these. This would be a ZX pi/2 of some sort. And then that eventually is what gets compiled down to your cross resonance or these are the pulses that generate the Bell state. Okay, so clearly you have an advantage in circuit programming because you have like 4 lines here to define this, whereas if you want to define your whole pulse library, you have to define the 9 pi/2 rotations for your XY cross resonance, your frame changes, your Hadamard in terms of those, your cross resonance in terms of all those gates, in order to build all these things up in this measurement schedule, which has kind of an, I don't want to say maybe not the friendliest user interface, but we're working on making this better as well. So and this gets into what I want to tell you about, is that we can define our own gates. So for example, if we know that we're already using Gaussian square pulses for our cross resonance, namely because we need a lot of energy because the pulse interaction is a lot weaker on the order of J over delta, so 1/10, 1/20th. So you need a lot more power or a lot more energy than the single qubit gates. So you can build your own CR pulse, and you can give it a duration, an amplitude, a sigma, and rise fall, which kind of give you a Gaussian on the ups and downs. You can create a schedule, and then you can look at the actual backend map, and you can just pull the instruction schedule map from that, which gives you the native gates that run on that particular piece of hardware. And then you can add your new CR gate to it, and you can add your CR gate to the new basis sets. And then you can start doing things such as appending your CR gate that you just constructed in a gate type way. You're adding the pulse to your construction, and then you can start doing process tomography, transpile that back down to something that would execute on the system and then fit your results. So this is kind of like one way, and this is exactly what they did in the paper, is they said, well, the calibration routines run certain experiments in a certain way to try and achieve the best gate fidelity. But what we're going to do is we're just going to try and do our own cross-resonance pulse in a couple different ways, do quantum process tomography and see how it turns out. And the results of it turning out, they did an echoed and non-echoed version of the cross-resonance, even without the rotary echo pulses. And we're able to see, pretty good ZX ZX results in the Choi matrices, where I think it's backwards. It's XZ because sometimes we flip the least denominator, the least significant bit. So sometimes the ZX becomes XZ. And then we can we can characterize that. In fact, some of what we do is called Hamiltonian tomography, which is consists of applying a larger and larger cross resonance pulse and then rotating around the Bloch sphere so that you can get an average. You're doing it a number of times for a number of amplitudes, and you can tease out the interaction terms in your Hamiltonian by doing this. So this ZX here is what you want. Of course, it saturates. It does not always go linear. It can saturate, it can come back, it can do all kinds of things. But mainly what you want to do is get rid of these other terms that are coming along for the ride. And they showed by creating this pulse, so just by starting with these kinds of schedules and with the quantum process starting in all the different states and measuring in all the different bases, you can work through the different amplitudes of this cross resonance and get, they got down to using just a single non-echoed pulse, it was 98.1%, whereas the back end one, which is the one that the fidelity of the backend gate that we return to you using all those tricks, is just a little bit higher. So that was a pretty cool thing, that they can just take a canned Gaussian square pulse and tune it up in such a way using open pulse. And so this is the kinds of thing that we're providing to, well, right now there's no multi-qubit system with open pulse. There's a single qubit public system. But now that CQT is in the IBM Q network, you should have access to a number of our 5-qubit systems have open pulse enabled on it. So these are the kinds of experiments that you can start trying yourself. Okay, so we still have a lot of work to be done, and I'll try and finish this in about 10 minutes or so. So for example, we know that the language that we're specifying, like this is OpenCASM 2.0. This is a little bit simple for the applications that we want to be doing right now. We kind of know we need to move into architectures that are a little bit more general, especially for doing certain kinds of problems, such as VQE, where there's a lot of would you say, near-term computing between the classical and quantum processors. There's also, the language right now is kind of separated, but the language for the circuit and pulse program needs to be kind of combined right now. Currently, they have their own types of objects called a CASM object and a pulse object, but these are something we're working on unifying. We're also looking at different kinds of instruction sets that will give us the kinds of range of flexibility for what we want. Coming up with different ways of scheduling that where you can easily incorporate dynamical decoupling, perhaps like rotary echoes or just like CPMG type echoing would be interesting. And I know a lot of our, some of our interns are working on dynamical decoupling, for example. We also have, hardware constraints such as maybe one of the gates isn't currently working, or there's something going on with the waveform generator that is causing things to fluctuate, and we need to be able to shut down 2 qubit gates between things that aren't working. So these are kind of open. These are being worked on all the time. We're always having new things come out, and so I wanted to be able to advertise one of those so I can give you a sneak peek of new features, because a new version of Qiskit is coming out this week, and it's going to have a couple things that are going to be very useful for Qiskit Pulse, such as parametric pulses. Well, you already had this parametric pulse. You could create the Gaussian, or you could create the Gaussian square and do the CR experiment. But what this does is it lets you query the backend and get the the way it is right now, you can query the backend and you can get the pulse that it's actually executing for the cross resonance. That's how you make all those plots right there. So anyone can do that. The problem is there's no way to take the parameters that were used to generate that pulse and then turn it into pulses that you might find useful. And those things might be very useful for, say, air amplification or rotary type experiments. So now what you can do is you will be able to get the parameters. So it will return the Gaussian square parameters, the drag parameters, all these other parameters, which are the same things that we specify pulses on our end. And so it's a huge data savings, and it compiles and runs the job so much quicker because you're only communicating a much smaller amount of data to our backends, which are then, can use that to generate the pulses just as they do if you weren't using Qiskit and I was just in the lab doing experiments. So that should be something very interesting. And then we have something new called the Pulse Builder, which is a bit more friendly, a bit more Pythonic way of building pulses. So this is very interesting because it makes it easier to design a lot of complex pulses. You can have nested contexts for complexity. So it's easy to build different timing alignments, different phases on your pulses, and changing the frequency. And so one of the examples I did here is an alignment where you can have a nested context, such as you want to align the pulses sequentially. So you can do a play pulse on your drive channel, so you get this pulse D0, but then you go into a new context where you're aligning pulses to the left. And so then you do a play pulse on the measurement channel, so you get this pulse, but then you decide you want to align channels to the right. So you do that, to the next control channel. And what this does is it aligns it to the right, but still to the left, left justified with that pulse before, but then the other pulse here is aligned to the left as well. So you can start making some very complicated schedules, and you can also do this with phases and frequencies. And then it will also give you access to the circuits and back-end dependent gates. So you kind of have the pulses that you can just start importing into your pulse schedule. So this will become available over the next week. I think it might have been up to a week before it was updated on PyPy, or however you pronounce the Python package manager. And then I just wanted to go through a few applications besides what I've talked about already. One of them is the error mitigation. So this is in particular a classical technique that we use a lot for VQE. For VQE, just as a summary, essentially what you're doing is you're asking the quantum computer to prepare a state, you're measuring an expectation value such as the energy, and then you're trying to minimize that energy by then having a classical optimizer prepare the next quantum state. So this is kind of really interesting because we just use entanglers here, so these are bare cross resonance. Essentially, you just need to explore enough of the Hilbert space in order for a classical optimizer to tell you the right direction to point in. With this error mitigation workflow that uses Richardson deferment to the zero, what it does is since VQE is not immune to incoherent error, what we try and do is we try to amplify the error. So if we had no error and we're just given our parameter C1 lambda, which is essentially given by the length of our gates that we're using, we know we have some minimum amount of errors, but we can stretch that error by essentially making our routine more vulnerable to decoherence. So we can do that just by stretching a pulse, but making that pulse do the same kind of thing. We can amplify the error, and then by doing enough experiments, we can then, by scaling that error in the right way, scale back to the limit where the error goes to zero. So it's very interesting, but this actually works. And this involves using pulse, and especially with the cross resonance, it's a little trickier because you want to use a linear regime of the cross resonance, or your parametric pulses are going to be very difficult to calibrate. But these are all things that you can do, and what's done in this paper. So for example, one of our VQE experiments looked at lithium hydride, looked at the bond length versus energy. So this is one of your go-to chemistry experiments. For the entangling, we could only do depth of 1 there because there was not much coherence. So this was actually the best results, was just doing 1 entangling step. So you're not really seeing yourself around the Hilbert space quite enough. But if you go to a depth of 3, then you could explore the Hilbert space a little bit more. Now the difference here is that you're going to suffer more for your nominal case, which is C equals 1. But if you do all these stretch factors and perform the Richardson's deferment to the limit, then you can extrapolate and get down to almost the exact correct answer, where this dotted green line has been done by exact diagonalization. So this is kind of a trick for taking the quantum hardware that you have and improving it by mitigating certain errors. And this kind of stuff is necessary, especially for the near-term noisy algorithms. Another thing that we have is we have measurement levels. So we have different ways you can acquire the information from the measurements themselves. So this is getting back to the acquire channel. And typically what you'll see from a digitizer, you'll see a waveform at the measurement frequency, around 7 gigahertz or so. Well, it's been mixed down to a IF frequency, probably tens of megahertz or so it can be digitized. But this thing will give you a kind of trajectory and IQ plane, and you can study this and classify these. But what we typically do, or what you can do yourself, is to specify a kernel or a way to integrate those waveforms in order to make your blob plots, which are your shots corresponding to 0 and 1 in essentially the complex plane. And then what you would typically do is you would discriminate those, and we have linear discriminant analyzers that will figure out the best way of telling the ones from zeros. But there's a lot of different ways you can do this using different kernel methods. You can try and come up with different ways of classifying your information. So while we have 1 and 2 levels are specified, and I think you can specify the kernel, one of the problems is the waveform data is so large that we're having a little bit of bandwidth issues getting that out right now. So currently measurement level 0 is not working, but this is something we can start using to, say, perform machine learning on state classification, for example, could be an application of this. And you can kind of see how this influences the readout fidelity by just looking at alternate lengths of your measurement pulse, because your trajectory and your IQ plane isn't getting far enough away from the origin if you're just doing a small pulse. But the longer and longer pulse you get, the more and more separation you can achieve. And then you'll saturate to some value, and then it will go back the other way, because you'll be hitting qubit coherence errors. And that's also especially due to the fact these are quantum non-demolition measurements. So if you measure a 1, you should be staying in the 1 state. And same with 0. You should be staying in the 0 state. So you can look at that analysis. And then there's another thing I was talking about, is we like to avoid the higher level states of the transmons, but sometimes they're useful for things. So if we decide we want to look at the 2 state, we can measure the transmon anharmonicity. This is something we have in our educational materials, such as the Qiskit textbook, how to do these kinds of experiments using spectroscopy, but you can do kind of anything you want to between the 1 and 2 that you do between 0 and 1. So there's ideas for using these new energy levels for generalized Toffoli gates. So you can expand your gate set, which could increase your quantum volume. There's other methods that are used. Essentially, you can get a lot better contrast if you try to do Rabi oscillations between your 1 and 2 state when you have an excited state population, and when you actually excite the state population itself, you can get a contrast to see get much better error on what your qubit temperatures actually are by calculating the Boltzmann factor. The measurement errors are so high you can't really get this between the ground and excited state without using the higher order state. And then I mentioned the leakage is one of these, and this is one of those recent papers where they used piecewise constant functions in optimal control on the I, which is the Gaussian, and Q, which is the derivative, to construct pulses that had a lot less leakage than the drag pulses you get. And I imagine that this lambda has something to do with the measurements of that drag. But essentially, they were able to get a very substantial decrease in the amount of leakage using like a 4 nanosecond pulse, which is really, really short for superconducting qubit control. And then, so in conclusion, like, we have all these device level metrics. The thing I wanted to say about quantum volume was those rotary echoes were essential in kind of compiling our arbitrary circuits into something we could run and eliminate enough interactions so that we can increase quantum volume. So it's not just happening from a hardware level, but it's also happening from a pulse control level. All of these things are becoming very important. So with the pulse, we can push our benchmarks and enhance our understanding and accuracy of near-term quantum computers among a lot of other fun control type things that you now have access to. So I guess with that, my hour is kind of up, so I can ask some questions here and then maybe move on to the into the chat room or whatever you think would be a good idea, Demetrius.
I'm here. I'm multitasking. So thanks for everything. Any more questions from the audience on this stage? I think that was quite nice. I have one. Okay. Jun, you just ask directly, Nick. You don't have to do privately. He's asking me, how can we repeat the error mitigation nature paper using Pulse?
Yes.
Just
okay.
we're a few people in the chat, so you can actually just unmute yourselves and ask.
Yeah, basically, we want to ask about this paper exactly.
Yeah.
Is it
yeah.
possible to repeat the whole experiment using Qiskit Pulse?
Yes, it'll probably take a while because you have to calibrate each one of these pulses a little bit better. One of the tricky things is I showed you in this Hamiltonian tomography is that initially back when we were talking about Hamiltonian tomography in an older paper, we were keeping ourselves in a linear regime because we thought if we kind of saturated the pulse, it wouldn't be a good idea. But then later on, we changed our minds and found out that actually for a general, if we just want to do a CNOT, then we can operate at a higher amplitude and we don't care as much about the linearity. So what the parametric pulses might let you be able to do is to just scale the cross resonance up in a linear regime without having to calibrate it as much. Or maybe you're close enough that you don't have to do rough calibrations and can do finer calibrations that are only based on error amplification, for example. So I think, the answer is yes, that you can completely do this same experiment, but it'll still take some effort, but it's possible.
Good.
That's cool.
Great. Any other questions from the general audience? This is the time.
Hi, this is James here. I'm based in Singapore. Great session. Hi. It's a curious question. I just wonder because I studied a bit on the Shaw algorithm on the breaking the quantum the RSA key. So I just wonder, have you ever tried, or does IBM ever tried to run Shaw algorithm on their Q network to try to break the RSA key?
Oh, well, the problem is using Shor's algorithm. I think the biggest number that's been factored by superconducting qubits was done by us, and it was 21. So your Shor's algorithm is so hard to do on the near-term systems because it involves a lot of control. I mean, just for RSA, you need at least 4,000, like current RSA, it's at least 4,000 logical qubits, and right now no logical qubits exist. And even at the error rates of the physical qubits, people think it might take, as little as 500 physical qubits to build a logical qubit, and that's with the current error rates. So, I don't think we're running Shor's algorithm as kind of proof of principle, and you have to, do a lot of tricks to be able to even factor 21 on the current hardware. So it's a cool proof of principle, but it's not really, like a business plan. Like there's not really a business model in factoring large numbers. So I think we're looking more towards this chemistry, which is kind of why I show this kind of VQE for chemistry and optimization is kind of what we're expecting more near term.
Okay, sure. Thank you.
Right. Anybody else?
If you don't mind, I just like to ask one more question. Where does IBM stand in terms of a qubit, in terms of the number of qubits that you can actually put onto your quantum computer? And what is the roadmap in the next few years to increase more qubit? What's the development plan?
Yeah. So, I mean, I think one of the things that we've talked about is quantum volume, and we've I guess, committed to doubling that every year.
Mm-hmm.
And that, right now is more limited by the errors than by the number of qubits, but you also need, to know that you're not going to hit any like kind of engineering challenges as you build larger and larger systems. So I think you'll continue to see, like right now our largest system is 53 qubits. I mean, I expect that number to keep on continuing to increase as the quantum volume increases as well. And it is because important, I mean, just the control challenges in scaling from like 53 to 1,000 or something, all the kinds of hardware that you have to swap out between, what we are doing for 53 is you have 53 coaxes on the input or something, for example. That's a lot of coaxes. But I don't know if you could fit 1,000 in a fridge, for example.
Right. I mean, I understand the challenges of tackling all the challenges of the interference and noises. Yeah, it's not easy.
Right.
Yeah, thank you.
So I think you're always trying to be in the situation where you're trying to decrease the noise, maybe on smaller systems, maybe not on your larger systems, while building larger systems that don't suffer from a bunch of noise problems.
Sure. Thanks for sharing. I appreciate that.
No problem.
Great.
Hi.
Can you please state your name and your affiliation, where you're from?
Hi, I'm Yap from CQT.
Hi, Yap.
Hi, Yap.
Okay.
Thank you for the nice talk.
Thank you.
I have a question. If we want to implement Qiskit on our own backend, how do we do that? Because I imagine there's a lot of lower level interfacing commands that we need to do, which are not actually visible on this level.
Actually, so basically it's not that hard. What Qiskit will turn over to a backend is something called right now it's a quantum object, and that quantum object has been kind of classified as a QASM quantum object or a pulse quantum object. But really, at its heart, that quantum object is just a Python dictionary that specifies all these pulses or all the gates that you want to operate, and then have maybe your backend compile down to something else. So that's kind of like why this parametric pulses it's a little different to make, because we can use the same construction of the pulses, but we can have our backend do it, which tends to be a lot faster than sending a whole long waveform over the internet via pulse to the backend, and then just taking that raw waveform, for example. So really, your backend just needs to be something that can read read a Python dictionary. Usually I think it's a JSON file. You can see what these are for Qiskit. We have something we call schema, which are essentially the specification of the of all the parameters in that you use to pass that quantum object around. And these are updated and consistently documented on the Qiskit website. They were first referred to in that Open Pulse and Open QASM archive paper that was kind of the precursor to what I was talking about today. If you want to then start doing things like, well, that's sending around JSON text files is not really the most efficient way of getting data around, then you might want to compile that into ASCII, move it across the internet, decompile it. But you can, it's not very unreasonable to think of having your own backend. Like if you wanted to write your own simulator, for example, you could have Qiskit control it by just telling Qiskit where to send that quantum object and then how to pull data back from it. And Qiskit is running on a number of backends that are not even, not IBM controlled, for example. So we're used on Honeywell's ION system and AQT's ION system, and QTech has a publicly available superconducting system and spin system, which are accessible via Qiskit. So I mean, we try to make it as easy as possible for it to run on your own backend, because we think it's a really good open source platform, and we were putting a lot of work into making it do what everyone in the field kind of wants it to do. So we're making it useful so that it's used on everyone's hardware, not just ours.
Great. Thank you very much for that, Nick.
No problem.
I think it's probably a good time to end now, unless there's any edging questions, last minute questions. And thank you all for joining in again. Next week or the week after, I think it's next week, we continue this time with ETH, Andreas Wallerf, again in superconducting qubits. And see you soon. Thank you.